Hello, I'm Frederick Kautz. I am the head of Edge Infrastructure at Doc.ai.
Hello, this is Nikolay Nikolaev. I'm technical lead in the office of the CTO for Kuma at the Kong.
So today we're going to go over a few topics. The first one, for those of you who are unfamiliar with what is network service mesh, and then we're going to go into a new set of things that we have been working on. So we have a new SDK, we have a new use case that we have been working on. We have integration with multiple CNCF projects, and we'll discuss what we've been accomplishing. So, Nikolay, can you describe a little bit about what network service mesh is?
Yeah, network service mesh is different things to different people. When it was designed, the project was targeting the developers, operators, and network function vendors point of view. So from a developer's perspective, it makes developers' lives easier because they just ask for connectivity and they work with high-level primitives. They don't have to bother with the details of networking, which usually is complex and hard to work with. From operators' perspective, you actually again you can conceptualize about these small details that usually the operators have to deal with. So it's easier to automate and to do all the lifecycle management of your workloads. You can also easier isolate them. You can easily monitor. That's also one of the goals for network service mesh when it started. And from network function vendors point of view, here we have an example of firewall vendor. You can actually focus on the functionality, on the business logic of your function. You don't have to worry how it connects to the rest of the world, which typically was a big problem back in the days. Now with cloud native and with network service mesh, this is not so. But overall, if we have to complete this slide, network service mesh gives the right tools to actually apply cloud native in the traditionally hard to manage networking world.
So one of the things that we've been working on in network service mesh is we've been working to simplify the overall system. And so before we had a code base that was disjoint from the work that the vendors would use. So in other words, the vendors who are building a network function would use a different set of APIs than the people who were building the actual network service mesh infrastructure and application itself. And so what we've done is we've rewritten the network service mesh system itself within the same SDK, within the same set of APIs, so that the same APIs that we are asking people to build the network services on is the same API that we are building the network service manager, the discovery work, the authentication and authorization work. So it ends up being the same code base. And what's nice about this is that this ends up setting the system up so that we run into the problems first ourselves, and we are able to get a higher quality of a system before we ask other people to go and build on that API. And we ensure that people who learn how to build the network services that are integrating in firewalls, it also makes it very easy for them to come back in and contribute, because once they understand how to build a network service, then they understand how the internals of it work, and how does the authorization work. Of course, there's details that they may have to read, but it's a much simpler pattern, and they understand the architectural pattern with once they understand how to write a network service itself.
Mm-hmm.
So this is the network service API, and so we have everything that we do is a gRPC API. So we start off with at the very top, what is the network service? And it comes down to two primary calls. We have a request and a close. A client can make a request for a service and a client can close a service. And simultaneously, the same thing is true about responses. One of the things that we have done as well is when a connection is established, we return a connection object, and so that connection object gets passed through the system. It gathers context like a snowball, and once the system has enough context to complete the establishment of that connection, that same connection context gets returned back all the way back to the user, which includes information which may have IP addresses, DNS, may have Ethernet information if you're dealing with L2, may also have information about who you've gone through with cryptographic tokens that demonstrate that you've gone through a specific set of firewalls, you've gone through a certain VPN or so on. And this also, by passing those cryptographic tokens through, it also gives you the capability to reason using your authorization system can reason about what's within those tokens. And so the API is a little bit richer than what we've shown here, but these are the core APIs that represent the heart of NSM.
I would like to outline one very important thing here in the API. It's the path and the path segment on the left. So this is a relatively new concept that was introduced recently okay, not so recently already, but was kind of new to NSM. It is inspired by some of the more lower level networking concepts, but is brought to this new high level gRPC API, much easier to consume, much easier to process. Essentially, it gives you an idea, like from a vendor, like a network service vendor point of view. When you get this path, you like the implementation knows where it actually this packet or actually its connectivity is going to pass. Who are the other players in the system? If you need to know that, and for people that have built networking solutions in the virtualization world, are familiar with the service function chaining, or as we prefer to call it, service composition. Here in NSM, this is really important improvement and information that you can have at runtime.
So here we have a very basic example. This is an example of a gRPC client, and that client is connecting to a network service manager and is making a request for a network service. And so you can see the request object being created using the standard gRPC path. We ask for the name. That connection has been established with SPIFFE and SPIRE, which we'll get into soon. And you can see the request has been made, and the response is from gRPC as a connection or an error as to why the connection failed. In the top, you can see the general flow of how this ends up looking. You see a request come in from the pod, from a client, goes to NSM. NSM will forward that request to the network service, and then we'll configure the data plane in order to make sure that the pod and the network service are capable of communicating with each other. What's key here, though, is that NSM itself does not sit in the data plane. It sits in the control plane. So NSM does not slow you down in the data plane if you have a faster data plane that you want to bring in.
Also, when we conceptualize here, when we say NSM and data plane, when we talk about control plane, it's a key thing to mention that it is a distributed one. It's not a central, it's not like the traditional SDN software-defined networking control planes. It's a distributed one, very much in the in the concepts and inspired by the concepts behind cloud native. The same is for the data plane. It's not a single entity. We're probably not going to go into details. You can go and check out our docs and see how it is implemented, but essentially it's a distributed one.
So in terms of how these are set up, so we described that network services uses the request and close API, the same API as we use internally. So we have here what's called a network service, we call it a chain. So the chain, in the case of a client, when that client was called saying, I want to connect to something, the connection goes through a series of microservices that literally follow the exact same gRPC API that we showed you before. And so we have authorize as a gRPC service, set ID and heal and so on. But they don't connect out to the outside world. They simply reuse the API mechanisms itself, the actual API interfaces. So these are all internal services that are within the process. So the system will run it through an authorized service and then a set ID service, a heal service, and each of these have been componentized and have been isolated from each other, and that connection object passes through each of these before it gets emitted to the network service manager, which then runs it through its chain, which includes the authorized, the token generator, doing discovery, and so on, and finally running through the connect, which then itself goes through to the endpoint, which then itself goes through the entire set of things that are like authorize, monitor, making sure that there's a timeout for the connection, and so on until it finally reaches the additional the additional functionality which represents your network service, which is the thing that configures your firewall or configures your data plane. And so this pattern is followed over and over again, and so when we said that we're normalizing and making it follow the same pattern, like we really do mean it. Like this is a pattern that allows us to make sure that we have things that are easily isolated, that we can easily test, we can reuse in other components. You can compose the things that you want or don't want, leave out the things you don't want, and build out a network service that allows you to also replace portions. Like if you don't use the same authorization that we use, maybe you have your own service. If you can write that microservice, or if your vendor provides one in the future, then you can plug that in and off you go.
Interesting fact, this whole idea started back in 2018 at KubeCon Seattle, where we were trying to design the very first version of the SDK. And then we ended up with so good design that we decided that the whole project should be slowly migrating to the idea of chaining components. So, yeah. Oh.
Cool. So we have here an example of some code that we pulled out. So this code, what it is journaling specifically. So it's not IPAM as the example says on the top. It's journaling. And so what we're doing is we're taking a result from IPAM, and if you look in the first step is creating a new server, and that new server is now living within the within your service, your endpoint. Then when the connection goes through this, the very first thing that it does is, you can see on the right hand side about 5 or 6 lines down, you see this connection comma error is equal to next server request. And so what that is doing is it's forwarding, it is evaluating the rest of the request first and sending it through the chain first. And when it gets the response back, because it itself is a client, so when that connection comes back that's been resolved as a client, then it's going to look at the information. It's going to introspect it and say, what IP address did you get? What seeders were in there? What connection paths did you have? and it's going to then publish that to NATs. And so this specific one was designed so that we could have IPAM, and you could use whatever IPAM you want, and then you could stick a journal on top of it so that if your IPAM ever fails, then you can, using yet another service, replay that set of decisions through your IPAM and get you that resiliency in an easy way without having to mix together the journaling and the IPAM together. So it makes them split out, it splits them out in a nice way that allows you to have the same mechanism, the same set of code that interacts with any form of IPAM that you want. And so we wanted to show this as an example of the API and how simple the API itself can be, and as a working example. Well, so Nikolay, we have this virtual L3 use case that we've been working with. Can you describe it a little bit for us?
Yeah, apparently it turns out that it's this is a very common use case, and once it was shown, we got a really big interest, people coming and talking to us. The virtual layer 3 is effectively being able to build a distributed virtualized layer 3 connectivity. For example, for things that you can build high level, like interconnection of higher level service meshes, like we have Kuma here and Istio, given as an example, but not only. We have seen examples with being able to sync databases across these, like cross data center database replication built on that, and other things. The basic idea is that you build out a set of small network service meshes, and you have kind of a gateway, which is not really the gateway that you would see in the traditional Kubernetes or other setups. It effectively is a very transparent one, but as you can see here on the picture, okay, it's a router, but effectively the idea is that it consumes the other remote routers as services. So it's a kind of like a service mesh in a service mesh. So you have your own network service meshes running in your clusters, and then the interconnectivity in between them is again a kind of a network service mesh on its own. And when these two concepts bind together, you effectively get a kind of a flat network, but also a controlled one. Like, it's not that each and every service in cluster 1 will see each and every service in cluster 2. It's only the members of the particular service mesh with the right security settings, right authentication set, and etc. This effectively allows you to build a set of such virtual layer 3 networks that can interconnect all these clusters, and in the same time they can work in parallel as if this connectivity doesn't exist. So the workloads that live in one of these virtual layer 3 won't see like the services won't see the other services, and this actually unlocks a lot of other use cases. We have seen people that are building much more complex solutions, and I'm sure Frederick can give better examples here. But essentially, everyone that was trying to interconnect data centers and distribute services have stumbled upon the obstacles of how do you interconnect, what's the IP of this data center, what's the subnet in the other data center, are there conflicts, which DNS I use, and etc. And with this, you effectively get a unified view cross data center of the same network, and your workloads can consume the same DNS server, and etc. etc. So that's kind of the high-level overview of what this use case is about.
And a quick note, so we have a core DNS plugin that we've linked in here. So our community created this plugin. It's called a fan out plugin that's designed to take multiple DNS servers and allows you to make a call to a specific one and then has them fan out the request to others and then fan them back in. And you can control that dynamically. So you can add and remove servers as you add and remove networks within your system. And so one of the next steps that we are going to accomplish in the near future is the injection of that DNS information into network service mesh. So we already have something to pass the DNS configuration in and out, but making sure that it works within the VL3 use case so that we solve not only the L2 and L3 use case of getting that connectivity, or specifically the L3 connectivity in this scenario, but we also solve for the DNS problems that, or at least give the tools to solve those DNS problems that are part of a complete L3 solution.
Mm-hmm. One addition that I would like to add here is when we say clusters, it's not necessarily only big data centers. It could be an edge, the deployment of workloads, etc. So it's a kind of a way to unify your distributed infrastructure. So it's not necessarily connecting big deployments. It can be a large number of small deployments. Okay.
Cool. So part of how we accomplish this, though, is that we also want to make sure that we accomplish what we described before, but also ensuring that we also maintain a good level of security. And so we start with the same cryptographic identities that the application service meshes use. And when we say application mesh, we usually mean L4 and L7. They're talking TCP, UDP payloads. They are manipulating HTTP. So network service mesh focuses primarily on layer 2 and layer 3, and you'll see a little bit more on this soon. We have layer 2 and layer 3 identities that get attested and get added. And the idea behind that is that we can cryptographically identify one service to another. And so we can cryptographically identify the thing that controls your firewall, the thing that controls your VPN, and make sure that when they can communicate with each other, that not only do they know who they are, but that we can then build that policy on top of them so that we have that cryptographic assurance that they are who they say they are. And we use Spire, which is the reference implementation of SPIFFE for that.
I think that this is a pretty revolutionary use of the whole SPIFFE and Spire, of course, as a concrete implementation of a runtime, because we're actually the traditionally when it was designed and the additional way that it's used in other projects is that you actually do this authentication on the higher level, as you said, layer 4, layer 7. But here, we're actually doing it at much lower level, the connectivity level, and effectively, this is a new way of using the whole concept. So, it's a good.
And so, when we look at how this ends up working, and so we have this broken up into 2 slides. So the first part is we have this separation of control plane from your data plane that we mentioned before. So you have something that you have your pod that has your application. You have your firewall endpoint that controls your firewall, your intrusion detection endpoint that allows you to control your intrusion detection system, and et cetera, as you go down through the chain. So there's a separation between control plane and data plane that exists here. When we start looking at how to do this, how do we integrate SPIFFE? What it looks like is something that looks like this. Every major service gets an identity. So the firewall has an identity. Your intrusion detection system has an identity. So when the pod makes a request for secure corporate intranet access, these are the identities that the operator can say the system must traverse through in order for that service to be rendered, in order for that service to be successfully connected.
Mhm. One of the interesting things here is that actually some of these can be hardware accelerated or even implemented in hardware. So effectively, we can say that with NSM we unlock the ability to um, use SPIFFE on hardware accelerated resources.
Yeah, and possibly in some scenarios, not only bring it down to the hardware for that performance, but also in the future, it should be possible to have if you're running your network services on in Kubernetes itself, you should be able to actually tie them down to the TPM module, and so that you can verify the hardware that it's running on indeed came from you as well. So there's a lot of really interesting work that's going on in SPIFFE that is above and beyond this. It's cutting edge. So there's new work that's going on with transitive identity, and new work that's going on towards how to federate SPIFFE trust domains together. So there's a lot of more interesting work that's coming out of this, and we're hoping. Not hoping, but we're in the process of helping them work out what some of those things look like as well within those communities. And so finally, when you do the connection, this is what it ends up looking like from an attestation perspective. You have your app, your VPN gateway. Those have their SPIFFE identities. You have a trust between the two organizations. So this gets you the ability to multi-organizational trust with SPIFFE and Spire for your workloads. So the last thing to really tie these things together is Open Policy Agent. And so I pulled an example from the repository and from NSM itself. And what this policy is doing is it's checking, is this token, the tokens that come in, so a token that represents the identity of everything that it's gone through, are the tokens expired? So what we do is we run them through through a thing that says tokens expired must be false. And that's the last line in the Go code that you can see here. And so this allows us to create that policy using something that's declarative and create advanced policies that are backed by data, backed by databases, and are able to be changed over time in a controlled way. So policy becomes pull requests. And so this is making use of Open Policy Agent, which is another CNCF project. SPIFFE and Spire are CNCF projects as well, and so we're integrating these things together in order to provide that cryptographic secure policy.
Okay.
And tying it into the previous graph that we see, these are the places that we have injected Open Policy Agent. So it's not just the connection on the outbound, but also the connections on the inbound. Like the client also has to ask the question: did the server render something to me that I trust, that fits my policy? So you have policy from the server side, you have policy from the client side, identity on the server and the client both validating each other and ensuring that they indeed follow policy. So with that, we want to thank you for your time and for hearing what's new within the network service mesh community. Feel free to come join us. We have the links here on how to join in. In the community section, we have mailing list, we have Slack. Our Slack community is very active. If you post a message on the Slack community, you're very likely to get an answer quickly. And we also just had NSMCon EU, which just happened. The videos, if they're not posted already, they will be posted in this location. So come find it over here. And as of now, we have all of our weekly meetings at 7:30 a.m. for the weekly developer PR meetings, and at 8 a.m. Pacific every Tuesday for the general NSM meetings as well. So please come and talk with us. Join us in Slack. Have conversations with us. And we will be around for a few more minutes to answer questions. So thank you very much.
Thank you.
Hello.
So let me check with our sound engineer. I can be heard properly, right? I can see in the chat. Anyways, just a little housekeeping. So the Slack community I mentioned is pound NSM in the CNCF Slack, which many of you have already joined. And also the event videos from NSMCon EU are already published, so you can go and see them through there. Let's see, in terms of the questions. So the first question is, I'd like to write my first app that uses NSM. Your slides show Sarah's app. Do you have sample code that implements a simple app that I can use as the basis for building my own simple app that makes use of NSM? Does such a repo exist in GitHub? So what I showed you right now with the SDK is something very new that we've built. We have an older version of NSM where we have an examples repository. And I will post that example repository in Slack in a short while. But there's some examples there that you can follow that'll be very close. So there's two levels of integration that I expect to see very common, at least in the Kubernetes space. I'm expecting there to be pre-canned apps, like if someone wants to connect two things together that are in different clouds, that's primarily a configuration thing. And so we want to be able to have NSM basically do a Helm install on it to get the things running that you need, and then you request for the service after you've done some basic configuration, and it just works. The second thing that we are expecting to see is we're expecting to see people eventually build out their own custom set of services. And the place to look in that, I don't think I have a good way to show this particular part off, but I'll post another link on there that shows the code that I showed before that showed a chain. You can build off the same set of patterns. So you would start off with a network service endpoint chain. You would implement your network service using the API, and then when you instantiate that chain, then that chain will then make use of all the machinery that we showed just now, and will also run your section of code. And I'll link to where that chain is as well, so that you can see that how that works. In terms of the new SDK, we should have it all up and running pretty soon. There's a couple more things that we have to work. We do have it working. We have traffic flowing between systems using the new SDK, but there's a few things that we need to do in order to make it usable so that people can start building on it. So thank you very much for that question. Let's see, I don't see any other questions, so we still have a few more minutes. So if anyone wants to ask any other questions, then it'd be fantastic, and I'll get you an answer. Yeah, we'll stand by for a minute or so. Oh, great question. So next one, what is the relationship to other projects? So other projects, the projects that I showed, I assume you mean the ones in the video. So the other projects that we discussed were SPIFFE and SPIRE. SPIFFE and SPIRE. SPIFFE is a specification on how to rotate identities and attest them. SPIRE is a reference implementation of that specification. And so SPIRE is a CNCF project, as is Network Service Mesh. And for those of you who are unfamiliar, CNCF is the parent organization of Kubernetes. So we're all sibling projects. Simultaneously, there's also Open Policy Agent, which is also another CNCF project. And so these particular projects are they're loosely coupled in that they don't require each other to run. In fact, NSM does not require SPIFFE, Inspire, or OPA to actually run, but we've implemented them in default implementation. So that so that's how that particular part is, like the relationship between them. Now there is another thing. So an additional question on top of that is, what about things like daemon and Multis and similar? So NSM has a different set of goals from them. So groups like daemon from Nokia are designed to create a interface that is within a pod. Like that is their primary purpose, is to be what's called a CNI multiplexer. NSM is orthogonal to CNI. And in fact, it's also unopinionated about whether you decide to use a CNI or not. So you could integrate NSM if you choose to do so. And I have a working thing with that, or rather, I have something that I'm going to be working on soon, which hopefully will show such an integration. But basically, showing the setup of a DANM or a Multis network in the custom resources and APIs that they provide. And NSM then focuses on the high-level stuff, like how do I connect these pods together, or how do I create the service function chain together across systems, or how do I configure the SDN to do something special based upon the requirements provided by the operator. So to be precise, daemon is specifically about how do I land using a CNI plugin, a secondary interface in my pod, while for network service mesh, that's a implementation detail, and we're working to coordinate what happens around and enabling the machinery behind that interface through the configuration of other SDNs or other resources. So hopefully that answers the question, and I want to thank everyone for your time. And feel free to reach out to me. We're in channel 2-KubeCon-maintainer. There is a thread where we can continue these conversations, and simultaneously also come join us in the NSM channel within CNCF Slack. Take care.